Welcome to video lecture M3. This one is on linear transformations in theory. I'll be your guide on the side, Tom Roby. Here are the outline and objectives. We'd like to characterize linear transformations independently of matrices as simply being functions from r to the n to r to the m that satisfy two basic axioms. Then by the end of the lecture, we'll prove that every linear transformation from r to the n to the other m can be represented, in fact, uniquely by a matrix. So at some level, linear transformations and matrix transformations are the same thing. But the abstract point of view actually is extremely productive for us later on in the course, where we want to think about a matrix transformation with respect to a different set of coordinates. And so we need to be able to think about it abstractly so that we can, take it and then rewrite it as a different kind of matrix that helps us understand the original matrix better. So that's coming up. But for right now, I'll just start with something very basic, which is that if you think about matrix vector multiplication, if I multiply a matrix times the sum of two vectors, then I have this distributive property, right? This is the same as a times u plus a times v. And why is that? Well, remember that a times u, by definition, just means take the u linear combination of the columns of a, right? The linear combination of the columns of a using these values u1 through um, right? Now, if I add that to the linear combinations of the columns given by v1 through vm, well, I could have just added u1 plus v1, u2 plus v2, and made that linear combination of the columns of A, which is what this is saying. So this is clear by the definition of matrix vector multiplication, just from the usual distributive property for ordinary numbers. Now here I've got a matrix times a constant times a vector, and the same kind of reasoning will apply to show you that this property holds. So there's nothing very exciting going on there, but we're going to abstract this out as a definition. So this is the definition of a linear transformation. So we'll call a function from r to the n to r to the m, any function, linear if it satisfies the following two properties. T of u plus v is equal to t of u plus t of v, and t of c times v is equal to c times t of v. Okay? So it preserves addition and multiplication by scalars. So let me give you some examples of things that are linear transformations and some things that are not. So here's a nice example of something that we'll see is a linear transformation. I'm going from R3 to R2, so I take a length 3 vector, which I'm writing horizontally instead of vertically like we might usually do. And its output is a vector of length 2, so in R2. And I want to show that this satisfies, say, property A. Property B is similar. So let me just show A. And so what I'm going to do here is say, all right, well, what is t of x plus y, right? Suppose I take t of the sum of two things. What do I get? Well, that's going to be t of x1, x2, x3 plus y1, y2, y3, right? And now I know how vectors add. I'm just going to write it all the way over here so that I have enough space. How do vectors add? They just add component-wise. So this is going to be t of x1 plus y1, x2 plus y2, x3 plus y3, right? That vector. This vector sign shouldn't be there. That's just an ordinary number. OK, so now what's that? Well, now I plug it into my formula, and I see, OK, when I apply t, what do? I take the second component minus the third component. That becomes my new first component. So this is x2 plus y2 minus x3 plus y3. Maybe I'll put parentheses here, 2 comma. And now I take the first one, x1 plus x2, and I add to it plus 2 times x3 plus y3. OK, so it's the output of this length 3 vector, this length 2 vector. And now I want to show that somehow I end up getting t of x plus t of y. So I need to split the x's and y's up. But that works just fine, right? Because what I'll get here is, OK, this is x2 minus x3 plus y2 minus y3 in the first component. In the second component, I'll have x1 plus 2x3 plus x2 let's see, this should have been x1 plus this should have been x1 plus y1. There we go. x1 plus 2x3 plus, let me switch colors here to see the correction, plus y1 plus 2y3. Okay, so now what's that? Well, now I can split these guys up and say, all right, so now I've got x2 minus x3, comma, x1 plus 2x3, plus y2 minus y3, y1 plus 2y3. And this just by definition is, the first thing here is t of x, and the second thing here is t of y. Okay? So what have I shown? At the end of the day, I've shown that just by using these definitions, that t of x plus y is equal to t of x plus t of y, which is property A. And you can show property B by a similar but somewhat easier argument. Okay? So that's number one. Let's look at number two. Well, what happens here is, now if you think about what happened in one, why did things work out so nicely? Well, one of the reasons they worked out so nicely is that everything that we had here was basically just a linear function of these individual coordinates of our vector. So that's going to be a good situation. Here I've got an x1 squared, and that's going to make things kind of wonky. And in fact, if you want to show something's true, you have to give a general argument like I did here. If you want to show something's false, the best way to do it is to give one single example that shows something's false. So to do that here, we'll say, all right, well, probably what I want to do is see what happens when I play with x1 in particular. And the easiest examples are usually the most convincing because people don't have to spend a lot of time doing computations to understand them. So here what I'll do is I'll say, I mean, you would play around to find this example, but suppose I take x to be 1, 0, 0, and c to be equal to scalar equal to 2. And now I'm going to compare what happens when I take t of 2x is equal to t of 2, 0, 0. And that turns out to be the only component here with an x1 in it is that. So it turns out to be 0, 4. Okay? On the other hand, if I look at 2t of x, right, well, that's 2 times t of x is just 0, 1. And that's equal to 0, 2. So since these guys are not equal to each other, it doesn't satisfy property A. So therefore, this one is not linear. And I don't even need to check any other property. If something's false for one value, then that's it. Game over. Right? So let's look at one more example. Suppose I have t going from R3 to R2 by this formula. So you might say, well, this should be good again, right? Because I've got, this is a linear equation, and this is a linear equation of the variables. And actually, you're sort of right, except that linear from now on in mathematics will often mean not linear plus constant, but linear with no constant. So as soon as you add a constant, it actually destroys this additive property. So for example, if we take something like x to be 1, 0, 0, and y to be 0, 1, 0, what's going to happen? Well, then we know that t of 1, 0, 0 is 0, 1, and t of 0, oh no, actually this is a different function. So t of x is equal to 2, 1, right? And t of y is equal to 3, 0, right? Because there's no x2 component here, and we have this, so we'll have 1 plus 2. All right, so now, what's t of x plus y? Well, that's t of 1, 1, 0. And t of 1, 1, 0 is going to have a 1 plus 2 here. It's going to be 3. And it's going to have 1 here. Okay? So t of 1, 1, 0 is 3, 1, but that's not equal to t of x plus t of y is actually equal to 5, 1, right? So these guys are not equal. So therefore, this fails. Right, and you could have seen that either of these two failed also by using property B, because in fact it fails for both of these properties. Now there is one other thing that you can use actually that can be helpful for testing certain things right away. Theorems are labor-saving devices. So what labor are we going to save here? Well, we're going to save the labor of having to, for part 3, we can save ourselves a little time, right? Because if a function is linear, then it has to be true that t of 0 equals 0, that if I plug the 0 vector and I get 0. So you notice that's true in each of these first two examples, although this one isn't linear for other reasons, but it's not true here. T of 0, 0, 0 is 2, 0. Okay? So why is this true? Well, here's the proof. There's nothing you can do to stop me. I'm going to say, well, t of 0 is some number, right? And whatever it is, it's certainly true that t of the vector 0, well, the vector 0 has this nice property that if you add it to anything, it doesn't change. So certainly that's t of 0 plus 0, right? And now by linearity, this is t of 0 plus t of 0. So now I've got blah, whatever this thing is, it's equal to itself. It's equal to 2 times itself. Okay, but now if I subtract t of 0 from each side, this implies that t of 0 equals 0. Okay, so it's basically a one-line argument. I didn't have a lot of space here, but I didn't need a lot of space to do that argument. So that's the first slide here. Okay, so we know by definition that a linear transformation preserves addition, which really means it preserves the parallelogram law for addition, right? So if we know where t sends, let's suppose we're dealing with a linear transformation from R2 to R2 because we can visualize those most easily by drawing two copies of the plane. So if we know that t sends 1, 0, if we know where t sends the standard basis vectors 1, 0, and 0, 1, then in fact we actually know where it sends everything, because any vector x1, x2 is just equal to x1 times 1, 0 plus x2 times 0, 1, right? So linearity is really useful for us there, because now we can do something like say, okay, and let me see, do I have anything else to write on this slide? No. So I've got plenty of space to write here. So what can we do? We can do something like say, all right, so here's my linear transformation. Right, so here's a copy of R2 for a domain. Here's a copy of R2 in the range. And now let's see. Maybe I didn't make the best color choices here, but so suppose I've got a blue vector, and this is 1, 0, which we sometimes label as the vector E1. And now we've got another vector, this orange vector here, although it may not look orange on your screen. This is the vector 0, 1, which is sometimes called E2. Right, now if I know where those go, then suppose I want to know where something else goes. So suppose I want to know where this red vector goes, which is E1 plus 2E2. Right, so if I go E1, that takes me out here. But now if I want to go out, let's even go out to 3E2. So I'll go 1, 2, 3. Okay, so this is about 3E2. And so now this point here, this vector will be E1 plus 3E2, which is, of course, just usually written as 1, 3. Okay? Now if I know where, I see I've written on top of my slide. Not so ideal. Anyway, so now over here, if I look at where these guys go, suppose my linear transformation, I don't know, suppose it rotates E1, so it does something down like this. So this is t of E1 is pointing down now. And let's say that t of E2 is, say, doing this now. So this is t of E2, right? Then if I want to do t of e1 plus 3e2, what does it have to do? Well, it has to be t of e1 plus 3t of e2, right? So all I need to do now is extend this guy out, e1 plus 3 of these guys, 1, 2, 3. So this will be whatever this vector is by the parallelogram law. Right, this vector is t of e1 plus 3e2, which is equal to t of e1 plus 3t of e2. Okay? So you can actually send the standard basis vectors anywhere, and you'll define a linear transformation from R2 to R2, as long as once you've decided where those go, you then just define everything else in the appropriate way. So the point is that so here, for example, 1, 3 is 1 plus 3. Those are the coefficients on that. So that's how linear transformations work geometrically. This geometric point of view is really useful because, you know, it helps us to be able to visualize these kinds of transformations. And there's this really nice applet that I directed you to earlier that I think is worth playing with some of these things and seeing where they go. So here's what happens in general. If we've got a linear transformation from R to the n to R to the m, then there actually exists a unique matrix. But the important thing is that it exists. There exists a matrix A such that applying this linear transformation to X is the same thing as just multiplying a vector on the left by the matrix A. You can always find such a matrix. And in fact, I can tell you exactly what the matrix is. All I need to do is look at this where the standard basis vectors go. Once I know where those go, I make those the columns of my new matrix. Okay, so these things, writing E sub j is the jth column of I sub n, well, here, by that I just mean I sub n is just the diagonal matrix. So for example, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. It's a square matrix, so this would actually be, for n equals 4, this would be I sub n, right? It's the matrix with just 1s on the diagonal and 0s everywhere else. And so if I take a look at the columns of that, the first column is the first basis, standard basis, second, third, and fourth. Okay, so that's all that means. All right, so how does this proof work? Right? Again, there's not actually that much going on, and you understand everything you need to do this. Right? You can always write a vector as x1 times e1 plus dot 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 plus xn times en. Right? That's really just what the definition is. And so by linearity, what can you do? Then I can say, well, t of x, once I've split it up into its components, this is sort of like figuring out what its projection is onto the x-axis, the y-axis, the z-axis, if you will. Right? So t of these things, well, first of all, by linearity, t of the sum is the sum. And now by the second property of linearity that I can rescale, these components, x1 through xn, are actually scalars, so they factor out. So I end up with x1 times t of e1 plus dot 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 plus xn t of en. And now what's that? Well, it's the linear combination of t of e1 through t of en given by the vector x1 through xn, which just gets written this way by the standard definition of matrix vector multiplication. So there it is. Nothing very deep, but very useful, very, very powerful actually when we start to apply it later on. So then this is just the matrix A, right? So all I do is make those the columns of my matrix. But I know this is a little bit abstract, so let's do a couple of examples here. So again, we'll work with matrices from R2 to R2, and let's say, suppose I want you to tell me what matrix is it that reflects through the line x1 equals x2, then scales horizontally by 2. So let's think about what that would mean. Okay, so I've got, so for 1 here, what am I doing? I've got one copy of R2, another copy of R2, and I'm reflecting in this line to begin with. So now I've got my basis vector E1, and I've got another basis vector E2, And what happens? Okay, so reflecting through the line, x1 equals x2, where does E1 go? Well, E1 actually goes to E2 when I reflect about that line. Imagine this is a mirror, right? And E2 goes to E1. But then, so E1 goes there, and then I scale horizontally by 2. Well, if E1 is now this vector, right, then scaling it horizontally doesn't do anything. So in fact, T of E1 is actually just equal to 0, 1. Okay. On the other hand, what's T of E2? Well, T of E2 goes to E1, but then it gets scaled horizontally by 2. Right? So this is actually 2, 0. This is equal to T of E2. So T of E1 is 0, 1. T of E2 is 2, 0. And I put those together in a matrix, and I get that the overall matrix here then is T of x in general is going to be equal to, well, 0, 1, 2, 0 times x1, x2. Okay? So look at where the first standard basis vector goes. It goes to 0, 1. The second one goes to 2, 0. And there's my matrix. Now, if I had had a slightly different linear transformation where I reflected about this line and then scaled both directions horizontally by 2, how would that be different? Well, then this vector would have gotten rescaled and become 0, 2, and I'd have 0, 2, 2, 0. Okay? So it's not hard to see what happens with the second one. All right, so now, what about 2? Suppose I scale by 2 and then rotate 45 degrees anti-clockwise, counterclockwise. So I've got my 2 copies of R2. And what happens? I scale everything by 2. Okay, so my vector E1 here, it's going to be something twice as long, and then it's going to rotate 45 degrees. So it's going to end up going out here. Now, when I rotate at 45 degrees, it's still something of length 2. But so then what are its components? Well, if it were length 1, then this would be, cosine 45 degrees, sine 45 degrees, so square root of 2 over 2 times square root of 2 over 2. But since I've made it twice as long, that means that the components here are actually square root of 2, square root of 2. So this is T of E1 is square root of 2, square root of 2. Now, on the other hand, if I look at T of E2, so here's E2, I scale it by a factor of 2, make a vector of length 2, rotate it 45 degrees, I end up over here. And by exactly the same kind of reasoning, this has coordinates. Well, this is negative x coordinate, right? So negative square root of 2 plus square root of 2. Okay, so then the final word is that the matrix here, T of x1, x2, is just given by, well, T of E1 is root 2, and then T of E2 is minus root 2. So it's really just the root 2 matrix times the matrix 1, 1, negative 1, 1. And you might want to think to yourself, like, what does this matrix do by itself? Where you just have 1, 1 and negative 1, 1. How is that different from this matrix? So, but I think that's all there is for this video lecture. Thank you very much for your kind attention.